Hello, everyone, and thank you for joining us today. My name is Renee Evelyn, and I will be your host for this NASA Technology Transfer Program webinar on NASA's new methods in preparing and purifying nanomaterials. Our presenter today is Dr. Diana Santiago de Jesus. Dr. Diana Santiago de Jesus is a research materials engineer in the materials chemistry and physics branch at NASA Glenn Research Center, working on the preparation and modification of nanomaterials for different applications. Dr. Santiago de Jesus earned both a bachelor's degree and a PhD in chemistry from the University of Puerto Rico. She joined NASA Glenn Research Center in 2010 and has been conducting research in boron nitride nanomaterials since then. Her innovative work is the foundation for the agency's direction in electrically insulating thermal management composite structures, directly supporting NASA's goals of developing electric propulsion systems for aerospace. In 2018, she became a technology development lead for the GRC hexagonal boron nitride nanotubes and hBN nanosheets research portfolio, a very exciting, potentially game-changing technology which promises to solve many heat and/or thermal management problems occurring inside of electric systems in both aeronautics and space applications. Earlier this year, she received the prestigious HENAC Professional Achievement Award in the government category. She's an active and passionate STEM mentor and contributes to many STEM outreach programs. Dr. Santiago de Jesus' work supports the Aeronautics Research Mission Directorate under the Transformational Tools and Technology Project and the Space Technology Mission Directorate under the Early Stage Innovation Program. Following Diana's presentation, I will be giving a short presentation on how NASA licenses technology to outside organizations. Before we get started, I'd like to point out that your microphones will be muted throughout this presentation, so if you have any questions, please type them into the chat box in the lower right corner of your screen, and we will answer them during the Q&A session at the end. And now Diana will present on NASA's new methods in preparing and purifying nanomaterials.
Hi, good afternoon, and thank you for your kind introduction. As she mentioned, I will be presenting this great methodology, specifically the intercalation and exfoliation of hexagonal boronitride. Next slide. Thank you. Hexagonal boronitride is a beautiful white powder as shown here in the picture that has become one of the most significant ceramics today due to its great properties and possibilities of applications in many different industries, including aerospace. That is the one that we are studying here at GRC. Among the great properties, there are good electrical insulation with a constant band gap of almost 6 electron volts. It has great mechanical strength and rigidity, also a very low density. It has high thermal conductivity with in-plane hBN having more than 100 watts per meter Kelvin and through plane around 30 watts per meter Kelvin. And in boronitride nanotubes, for example, it also has 600 watts per meter Kelvin carrying it through the length of the tube. So those are very high values. Hexagonal boronitride has a great stability by being chemically inert, starting oxidation above 1,000 degrees Celsius, and is also hydrophobic. These are great properties that have made boronitride a great candidate for different applications. Next slide. The motivation developing this technology started with the similarities of boronitride materials with carbon nanomaterials. One of them is like boronitride has several allotropes, amorphous, cubic like diamond, wurtzite, and hexagonal like graphite. And if you roll the structure of hexagonal boronitride, you get the boronitride nanotubes like carbon nanotubes. So how this started is when early in 2000, NASA GRC started working with boronitride nanotubes for ceramic composite applications to explore the properties. During that time, GRC developed a nice production of boronitride nanotubes, being able to develop like a lot of quantities by that time that it was very limited in the early 2000s. A few years later, Dr. Shin-Che Hong joined the team with his expertise working with graphite and the intercalation process, and also brought a lot of curiosity and questions to answer. The first question was, if hexagonal boronitride is similar to graphite, can we intercalate it and exfoliate it too? And at that time, it was happening the big boom of research work in preparing graphene and also to make them in bulk. So the next question was, can we make white graphene? So those are questions that we answer with this technology. Next slide, please. First, let's just start explaining what is intercalation and exfoliation. Intercalation is a physical process where a molecule is inserted between the layers of a 2D material like hexagonal boronitride. The insertion of these molecules can expand the interlayer spacing, weakening the van Waals force, and changing the structure of the host material. As you can see in the sketch, there is a slight separation between the layers in comparison with the 2D material without molecules inserted. Not too much, but just a little bit. The exfoliation process, explained in the third side of the sketch, it is a delamination process where the layers of the host materials are expanded from the normal distance until there is a clear disruption of the layers which gets partially separated. This process can break the van der Waals force between the adjacent layers by exerting certain external force, a strain that in this case is shown here in the sketch by is the formation of particles that get bigger and expand the layers of the host enough to separate them. Next slide, please. So the exfoliation behind intercalation with iron chloride was tried on hexagonal boronitride, but it doesn't work like the same way with graphite, just adding iron chloride to the boronitride. It needs an activation agent, and this is due because of how chemically inert is the hexagonal boronitride. The general methodology is shown here. You add boronitride, hexagonal boronitride, iron chloride, and an activation agent, apply heat, and then you obtain the intercalated product A. If you take that product A and apply heat again, the iron chloride becomes iron oxide while expanding the layers and exfoliating the hBN, and this is product B. You can take the product B and repeat the intercalation, then exfoliation, and any of these products, the product A, B, C, D, you can clean them with hydrochloric acid and obtain a clean, beautiful white product without any impurities or intercalates, different kind of products. And this is what we call the original process. So Shinche also developed a second process that is the same one, but after the intercalation process, we do a hydration process in wet air. The intercalated hexagonal boronitride get hydrated, and then you exfoliate that product, and that's the method, the second method, the hydration method. And then you can clean the product and obtain white, clean boronitride at the end. Next slide. So in this chart, I'm showing you the different structural and chemical changes that are happening during the intercalation and exfoliation process. First, I'm showing you the XRD, where it shows the structural changes, where first in the blue line, you can see the original boronitride without any reaction. It has a sharp peak in the 002 peak, and the full spectrum show like a clean spectrum, just the two different boronitride peaks. When you intercalate the product A3, in this case, you see that the 002 peak decline considerably. In the spectra, in the full spectrum, some other products like iron oxychlorate in the spectrum with boronitride peaks. When you exfoliate this intercalated product, then the peak, the 002 peak decreased so considerably, and this is because a lot of disorder is being introduced to the lattice of the boronitride, and the peak almost disappeared in the bottom of the screen in the green line. And as you can see in the full spectra, you don't see anymore the iron oxychloride. You see the iron oxide peaks with boronitride. And if you, at the end, use hydrochloric acid to clean the sample, you obtain an exfoliated sample with clean peak, and the 002 peak is back to normal again, and this normal peak, smaller than the original one, but still the same kind of peak. And the full spectra show a total clean spectra, not any iron species there anymore. Sorry. In the FTIR spectra in the right side, and then you see like what all the chemical changes happening in the boronitride. You can see going from the normal hBN peaks, that is the black line on the top, going from two processes of intercalation and exfoliation, and then back to the clean sample after being exfoliated and cleaned by HCl. You see like the peak is back to normal to the original sample. All these changes, you see them in the stretching band in the around the 1300 peak in the stretching BN stretching, but in the other side, the BNB sorry, vibration bending peaks, you don't see that many changes. You don't see any visible change. So the changes are happening in the stretching band. In this other FTIR in the middle, you can see that the changes that are happening in the intercalation process are done because of the introduction of iron chloride to the sample. We show at the bottom a clean, dry bottom iron chloride, and in the top is the original boronitride, and you can see the intercalates are very similar to the iron chloride. Next slide. In this chart, I'm showing the SCM micrograph of different exfoliation processes. The first one is a backscatter image of the hexagonal boronitride with iron chloride. The backscatter detector helps to identify heavier elements from the lighter elements. The heavier elements look brighter. Here in the micrograph, you can see brighter edges and lines in the boronitride, demonstrating the intercalation of the boronitride with the iron chloride. We have many ways that we can do exfoliation that give the different products. If you take the sample and you do a slow oxidation, meaning that the sample was placed in the oven, and then the oven was turned on and increased the temperature slowly until the desirable temperature, you create, in the middle picture shows that you create smaller particles of iron oxide. These are nano-sized particles. And the layers of the boronitride are starting to get split in the 20 to 30 nanometers thickness. But if you take that sample and then do a fast oxidation, this means that we put the sample in a preheated oven that is already in the desired temperature, and when you put the sample there, and the iron oxide particles here develop like in the micron size, and the layers of the boronitride are a lot more separated. Here in the micrograph, in the top right, you can see that the sample after cleaning with hydrochloric acid has some layers separated from the bulk, and they are bended and they're a little bit transparent, and that's exactly what you are expecting to see with samples that have been exfoliated. A little bit of transparency on the layers. If you take the intercalated sample and do the hydration process before a quick oxidation process like the one that I just explained, then we obtain the same thing, like very big particles, micro-sized iron particles. And as you can see here in the bottom image, you can see the micron-sized particles are darker in color. In this case, we use a secondary electron detector. So you can see the iron chloride, iron oxide particles are darker in color, while the boronitride particles, you can see them embedded with separated layers, but embedded in the iron particles, big particles. So in the other image is a zoom in of an area where you can see the separation of the layers. They are very small, thin layers, and they are separated. These are, I really love seeing this micrograph because it shows exactly what this process does and the different ways that you can exfoliate these samples. Next slide, please. If you want to produce a standalone hBN, what we call here the Boronitride nanosheets or the white graphene, you can repeat the same procedure that we just discussed many times as you want to decrease the thickness of the layers until you obtain your desired layers. Here I'm showing in the TEM micrographs layers that goes from 2, 4, 6, 8, all the way to 20 layers, and it is pretty cool to see that you can get all the way to 2 layers of Boronitride with this process. Next slide, please. Can this method work intercalating other materials? Yes, we can intercalate other materials. Here I'm demonstrating the intercalation of aluminum chloride. Why aluminum chloride? So it reacts very similar to iron chloride with hBN and using an activation agent. You have to use that activation agent. It produces alumina, which we are not able to remove, and that's exactly what we want when we add aluminum chloride. In this case, the aluminum acts as a functionalization of the hexagonal boronitride. One other procedure that we developed was the coating of the hexagonal boronitride with alumina. That is, also you can intercalate and coat or just coat the boronitride. And here I'm showing some pictures of the presence of alumina. We were doing some coatings and some intercalations with alumina in the hexagonal boronitride, and the XRD shows like the conversion from to aluminum oxide, the one that we were expecting. Next slide, please. What are the other benefits of modifying the hexagonal boronitride? In this case, with alumina, well, hBN sinters at very high temperature, 2000 degrees Celsius. And to make a puck, it is very difficult because our hot press here limit is 2000 degrees Celsius. So we cannot use it at that high temperature. And when we were finally able to make the puck that we needed, it just broke because of the shearing properties of hexagonal boronitride. And so adding alumina by intercalating and coating or just coating hBN, we can decrease the sintering temperature and make a more robust ceramic composite, like the one that I'm showing here in the picture. This was 20 on 80% boronitride, 20% alumina. This can be done because alumina sinters at 1400 degrees Celsius, and alumina has, it can complement the boronitride with its properties. It has very good thermal conductivity with 30 watts per meter Kelvin. It has good mechanical strength and chemical and physical stability. And while having hBN with alumina together also are demonstrating very good thermal shock, promising thermal shock results in some experiments. So here I'm demonstrating also like a sample with 60% hexagonal boronitride and 40% of alumina, that we were able to make a puck, and it was tested and meshed the thermal conductivity, and in plane, sorry, in plane conduction is almost 90 watts per meter Kelvin at room temperature, and through plane conduction is almost 20 watts per meter Kelvin. Those are very good values, and they decrease when they get all the way to 1000 degrees, but it is very impressive to see almost 20%, 20 watts per meter Kelvin of conduction through in plane in this puck, in this ceramic composite. So I also have to say that we can make pucks, very strong pucks, even having 90% of boronitride and 10% of alumina. Next slide, please. Is this method effective with other type of boronitride? Yes, it is effective. The most common ones that we use with this methodology, it is the Momentive PT110, that is 45 micron size in the particle size, and AC 6097, that is about 0.5 microns. Those are the most common ones, but we have also used other Momentive products like PT180, PTC120, NX10, and CCS 102. And also we have used boronitride nanotubes. Yes, we have used other type of boronitride. In this case, we use a commercial one from BNNT, and we use our own boronitride developed here in the center. Next slide. Here we show pictures of the commercial product. First, in the left pictures, it is as received material. You can see like a few walls, straight walls of the tubes. They are very tiny tubes, and our material is at the top to the left, to the right. When you can see our tubes are in diameter close to 300 nanometers, and they're more like bamboo style tubes. And sorry, we use the same intercalation and exfoliation process methodology developed with iron chloride. And in this case, it just opened the tubes and developed what we call the boronitride nanoribbons. And as you can see here in the second image in the middle, it's the commercial one. You cannot see the tubes anymore. They're just open. And the one from our in-house, prepared in-house, you can see a little bit of the shape of the tube, but they have a lot of layers opening. You can see how much the surface area of this tube increased. And at the end, these products were cleaner than the original ones. These products always, the original ones has a little bit of precursor materials or aluminum, a little bit of catalyst. And at the end, they were very clean materials and just hBN or boronitride nanotubes or ribbons. Next slide. Can the production be scaled up? Yes. But here, let me just mention first some of the advantages of our technique. The intercalation and exfoliation method does not have the constraint of using a mechanical method that can limit the scale-up process. Other processes to exfoliate hBN can break the particles in all different directions, and that's not what we want. This can happen by applying the mechanical forces, such as sonication or ball milling. Ball milling can contaminate the product by taking small particles from the media that then will be very difficult to remove from the product. These mechanical methods might be more difficult to scale up. So initially our batch was limited to 5 grams, and this is because of the size of the setup that we were having at that time. But since 2015, a new chemical reactor with temperature controller was engineered and to produce more than 30 grams per batch. That was a huge increase. We acquired recently a second reactor to do the diversity of research using this method, because we are so overwhelmed with all the different products that we can create and so many others that we want to try. So we needed to have another reactor. We need more manpower too. But there's a lot of room to increase the reactor size for even bigger batches. Next slide. So why to exfoliate hBN and why with this method? And I just wanted to explain a little bit why for us is so important. In some of our most important applications, we are making polymer composites with boronitride as a filler. We need these composites to be flexible, but we want the properties of boronitride to show, especially the thermal conductivity. So we need to create a balance between polymer and hBN, and this is very difficult. For this, we need this technique. More surface area. This technique can create more surface area. It can create less boronitride layers that reduce the phonon to phonon scattering, and that will eventually improve the thermal conductivity. Keeping bigger but thinner platelets will help we have a more effective conduction path in a lower value fraction of a matrix, and that's really important. So we need to have a technique that can create big batches of exfoliated boronitride. And we need to be able to tailor these properties for the specific applications. If we want to add like one other molecule, or if we want to exfoliate to a certain degree, that's tailoring properties for specific applications. So this method can give us all of these. Next slide. There's so many different applications that I have found that have been in use right now. The Boronitride has been in use right now, and many other more that Boronitride properties can fit because of the great multifunctionality of the Boronitride. We're working in aerospace with some of these, like the structurals and components, radiation shielding, electric propulsion components, and temperature ceramics and insulations, but also it's being used in electronics, cooling of electronic packages, heat dissipation in nanoelectronics. In rheological modifier, this is big, lubricants, adhesive, which can operate in vacuum at a high temperature, fillers for epoxy and other polymers, filler for cosmetics, that's one of the biggest one, for eye and skin care as a slip modifier, corrosion resistant in paints and coatings. In the medical field and health, drug delivery because of the chemical inertness, neutron capture, cancer therapy, water purification. In the nuclear also, neutron detector for geothermal and nuclear reactors. The applications are endless with these products. Next slide, please. A summary of the things that we have accomplished with this method is we can exfoliate the intercalation of iron chloride for different products by changing some methodology conditions. Exfoliated hBN, we can have different sizes of hBN platelets. We can, intercalate with iron oxide, nano or micro size particles, embedding hexagonal boronitride in big iron oxide particles. And also we can create iron nanoparticles, like metal iron nanoparticles. The one that I'm showing here in the picture, they were formed after iron chloride being intercalated. It was heat treated at high temperature with 5% a gas with 5% in hydrogen, and we created iron particles on hexagonal boronitride. That was pretty cool. We can use this product to create boronitride nanosheets or white graphene. We can create boronitride nanoribbons from boronitride nanotubes. This method was used to successfully intercalate other materials than iron chloride, like aluminum chloride, the one that I demonstrated, but many others like glass, carbon materials, small boronitride, and others. Intercalating and coating hexagonal boronitride with alumina also open new ways to functionalize boronitride and explore high temperature ceramic composites while decreasing the boronitride hot pressing temperature. We modify the chemical reactor design to increase the production yield by 6 times. And there are several investigations in progress optimizing the process with very exciting results, enhancing exfoliation in less steps. And that's what we want, to use also less chemicals. Next slide. What else can be done? Or meaning like what else you can do if you are interested in our technology? This intercalation and exfoliation methodology is very versatile and can be used to tailor hBN for different applications. Functionalizing and modifying hBN is a tedious process due to its chemical inertness and interaction and this intercalation and exfoliation methodology has demonstrated a way to tailor the properties for what your application needs. This method can be adapted to intercalate a wide variety of particles independent of composition, geometry, shape, and size. Scaling up the process for commercial purposes can be easily designed and built at an affordable cost. there is so much more to develop and discover with this technology if you are interested. Next slide. I want you to thank you for your interest on being here in this presentation. And I would like to thank all my team, Boronitride research team, especially the ones that work really hard on this technology, Chinche, Janet, and Marisela, and the new people working in our technology, Bashawa and Sean. Thank you all, and the rest of the team for helping me with suggestions for this presentation. Thank you.